There is something quietly strange about the number 1.672. Not because it sounds remarkable. It sounds like the kind of number that belongs in a footnote, buried in a table, ignored by everyone except the person who calculated it. But that number is the radius of a planet. A planet that, according to every model astronomers have built so far, should not have a dead density anywhere close to Earth's. And yet it does. Somewhere 100 light years from where you are sitting right now. There is a world that appears to be breaking a rule it was never supposed to be able to break. A world that is almost 5 times heavier than Earth, only slightly larger, and yet weighs almost exactly the same per cubic centimeter. For a moment, that might not sound like much, a coincidence of numbers, a statistical curiosity. But density is not just a number. Density is a fingerprint. It tells you what something is made of, without ever having to touch it. And when researchers ran this planet's fingerprint through every model they had, the answer that came back was not rock. It was not metal. It was something else entirely. Something that, if confirmed, would mean astronomers have found a version of Earth that took a different path. A world where the dominant substance is not iron, not silicate, but water, not a lake, not an ocean. An entire planet, a quarter of its mass, made of water. To understand why that single number matters so much, we have to go back to the beginning. Back to a satellite scanning a tiny patch of sky, watching for a flicker that most instruments would dismiss as noise. This is the story of TI-1452b. And by the end, the central question will not be whether this planet exists. It will be whether we have been looking for life in the wrong places all along. Every search for life beyond Earth begins with the same assumption. An assumption so basic that it rarely gets questioned out loud. Life needs liquid water, not ice, not vapor, liquid. A solvent stable enough and abundant enough to allow complex chemistry to organize itself into something that can replicate, adapt, and persist. On Earth, this story stretches back roughly 3.5 billion years to oceans that existed while the planet was still young, still being bombarded by debris left over from the formation of the solar system. Life did not wait for calm. It started in chaos, in water, almost as soon as conditions allowed it. That single fact has shaped the entire search for life beyond our solar system. If water is the prerequisite, then water is the target. For decades, that target felt almost impossibly distant. Planets beyond our solar system were theoretical, inferred, until 1995. Not a single confirmed exoplanet existed in the scientific record. Then the numbers began to climb, slowly at first, then faster. Today, more than 5,000 confirmed exoplanets sit in the catalogs, a number that continues to grow every year. Most of these worlds are nothing like Earth, gas giants larger than Jupiter, scorching hot from orbiting too close to their stars. Rocky worlds baked into airless husks, planets locked so tightly to their suns that one side burns while the other freezes in permanent night. But scattered among these thousands, a much smaller category exists. Planets that orbit at just the right distance, not too hot, not too cold. A region with an almost folkloric name, the temperate zone. The place where, if a planet has the right ingredients, water could exist as a liquid. Most planets found in this zone turn out to be disappointing on closer inspection. Too large, too gaseous, too uncertain. And then, in 2022, a signal appeared. A small, repeating dip in starlight, occurring once every 11 days, coming from a red dwarf star in the constellation Draco. At first glance, this looked like nothing unusual. Red dwarfs are common, small planets are common. The galaxy is full of these faint signals. But this one came from a system that, on paper, should not have been easy to study at all. To understand why, we need to look at where this signal came from, and why it took so long to confirm what it actually was. The satellite responsible for detecting this dip is called TESS, the Transiting Exoplanet Survey Satellite, launched by NASA in 2018. Its job is deceptively simple. Stare at stars. Watch for tiny, periodic drops in brightness. Each drop could mean a planet has passed in front of its star, blocking a fraction of its light. This is the transit method, and it has become one of the most productive tools in the search for new worlds. TESS scans a region of sky roughly 400 times larger than the area covered by its predecessor, the Kepler Space Telescope. More sky means more stars. More stars means more chances for a planet to align perfectly with our line of sight and cast its shadow across the telescope's detector. When TESS recorded the dip that would eventually become known as TOI-1 or 52b, the data alone wasn't enough. The signal pointed toward a star cataloged as TOI-152. The letter B indicated this was the first planet identified around that star. But there was a problem. TOI-152 wasn't a single star, it was two. A binary system, separated by roughly 97 astronomical units, a distance about 2.5 times greater than the gap between the Sun and Pluto. From Earth, even with a sensitive instrument like TESS, these two stars appeared as a single point of light, one signal, two possible sources. So the question became unavoidable. Which star was the planet orbiting? This is where the story could have ended in ambiguity. A promising signal, an unresolved binary, and no way to know for certain which star the planet belonged to. Instead, astronomers turned to ground-based observation. At the Observatoire du Mont Mégantic in Canada, a specialized imaging system called PESTO was aimed at the binary system. Unlike TESS, PESTO had the resolution to separate the two stars from each other. And when it did, the picture became clear. The transit signal belonged to the larger of the two stars. The planet had a confirmed home. A second team, working independently in Japan, examined the same data and reached the same conclusion. Two separate groups, two separate continents. One answer: the planet was real. It had a star. And now, the real investigation could begin. Confirming a planet exists is one thing. Understanding what that planet actually is requires a very different kind of detective work. The first clue comes from the transit itself. The amount of starlight blocked during a transit depends directly on the size of the object passing in front of the star. A larger planet blocks more light. A smaller planet blocks less. By carefully measuring how much the star's brightness dipped during each transit, researchers calculated the size of TOI-1452b. The result: a radius approximately 672 times that of Earth. That number alone places this world in an unusual category. Too large to be considered a true Earth analog. Too small to be a mini Neptune, the gas-rich category that dominates so many exoplanet surveys. It sits in a gap. A category astronomers sometimes call a super-Earth, a term that describes size, not composition. Because size alone tells you almost nothing about what a planet is actually made of. To go further, researchers needed a second number: mass. For that, they turned to a completely different technique, the radial velocity method. Here's the idea. A planet doesn't just orbit its star. In a sense, the star orbits the planet too, just on a much smaller scale. The gravitational pull between the two causes the star to wobble, tracing out a tiny ellipse as the planet circles around it. That wobble is too small to see directly, but it leaves a signature in the star's light. As the star moves slightly toward us, its light shifts slightly toward the blue end of the spectrum. As it moves away, the light shifts toward red. This is the same Doppler effect that changes the pitch of a siren as it passes by. Except here it's happening to photons instead of sound waves. By measuring these tiny shifts over time, researchers can calculate the strength of the gravitational tug, and from that, the mass of the planet causing it. For TOI-452b, the result came back at 4.82 times the mass of Earth. Now the picture starts to get strange. A planet nearly 5 times more massive than Earth, but only about 1 2/3 times larger. On the surface, that might sound like it simply means a very dense, very compact world, more mass packed into not much more space. But when researchers combine these two numbers, mass and size, To calculate density, the result didn't match that expectation at all. The density came out to approximately 5.6 grams per cubic centimeter. For comparison, Earth's average density is about 5.5 grams per cubic centimeter, almost identical. And this is where the investigation takes its first real turn. If you only had the mass, you might assume TOI 1452b is a scaled-up version of Earth. More rock, more iron, more of everything, just bigger. If that were true, the density should be higher than Earth's, not nearly identical to it. A planet built from the same materials as Earth, but with almost 5 times the mass compressed into a slightly larger volume, should be noticeably denser. Gravity compresses material more efficiently as mass increases. More mass should mean more compression, and more compression should mean higher density. But it doesn't. The density stayed almost exactly where Earth's does, as if the extra mass wasn't made of the same stuff at all. This is the moment where the comfortable explanation, "It's just a bigger Earth," quietly falls apart. So if TOI 1452b isn't simply a larger version of our own planet, what is it actually made of? To answer that, researchers built models. Not physical models, but mathematical ones. Simulations of planetary interiors that test different combinations of materials, rock, metal, hydrogen, water, ice, and calculate what density and size those combinations would produce. Each combination traces out a curve on a graph, a theoretical line representing, if a planet were made of this, here's how its mass and radius would relate. When researchers plotted TOI 1452b's measured mass and radius against these curves, the planet didn't land near the lines representing rocky Earth-like compositions. It also didn't land anywhere near the lines for gas-dominated worlds, the mini Neptunes with thick hydrogen envelopes. Instead, it landed in a narrow region, a region consistent with 2 possibilities. 1. A rocky planet with an unusually thin envelope of hydrogen gas. 2. A world where water itself is a major structural component, not just a surface feature, but a significant fraction of the planet's total mass. According to the modeling, if the second possibility is correct, water could make up roughly 25% of this planet's total mass. To put that in perspective, water makes up less than 1% of Earth's total mass. Earth has oceans, but those oceans are a thin film compared to the planet's overall bulk, a layer of moisture on top of a world built from rock and metal. A planet where water accounts for 1/4 of its mass is not Earth with bigger oceans. It's something categorically different. A world where water isn't a feature of the surface. It's part of the planet's fundamental architecture. There is a place in our own solar system that gives us a hint of what that might look like. Not a planet, a moon. Europa, one of Jupiter's large moons, is thought to be composed of a rocky core surrounded by a thick layer of water, much of it in the form of ice, with a possible liquid ocean beneath that ice shell. Europa's water content, as a fraction of its total mass, is dramatically higher than Earth's. If TOI 1452b's composition resembles Europa's, but on the scale of an entire planet, with enough internal heat and the right temperature conditions for that water to exist as a liquid rather than ice, the implications become difficult to overstate. This is the part where the investigation should, by all rights, slow down, settle into comfortable territory. A water world has been found, a planet with the right size, the right density, sitting in its star's temperate zone, where temperatures could allow liquid water to exist on or near the surface. But this is exactly where a careful observer has to stop and ask, how confident can we actually be? And the honest answer is, not very. Not yet. Density alone cannot tell you with certainty what a planet is made of. The same density can be produced by completely different combinations of materials. A planet with a slightly larger rocky core and a thin hydrogen atmosphere can mimic the density of a planet with a smaller core and a thick water layer. From the outside, using only mass and radius, these 2 very different worlds can look identical. This is the uncomfortable truth hiding behind that number 5.6. It doesn't prove water. It permits water. It's consistent with water, alongside other explanations that have nothing to do with oceans at all. So the question shifts. Not, is this a water world? But how would we even find out? And the answer to that question leads in somewhere unexpected. Not back to TESS, the satellite that found the planet. Not to the ground-based telescopes that confirmed its orbit. But to an instrument capable of something neither of those tools can do. Reading the chemical signature of a planet's atmosphere from 100 light-years away. The James Webb Space Telescope doesn't just collect more light than previous instruments. It collects a different kind of information entirely. When starlight passes through a planet's atmosphere during a transit, certain wavelengths of that light get absorbed by specific molecules. Water vapor absorbs light at particular wavelengths. So does carbon dioxide. So does methane. Each molecule leaves its own signature, a kind of barcode imprinted onto the starlight that passes through. By capturing that light and breaking it down wavelength by wavelength, Webb can, in principle, detect the presence of these molecules in a planet's atmosphere, even from 100 light-years away. If TOI 152b has a substantial water content, and if that water has any connection to the atmosphere above it, whether through evaporation, outgassing, or atmospheric exchange, Webb might be able to detect it directly. Not infer it from density. Detect it. This is where the story stops being about a number on a graph and starts being about an active, ongoing investigation. As of now, the deeper atmospheric characterization of TOI 452b, part of an ongoing effort, one of many temperate waterworld candidates that Webb's instruments are capable of examining. And this is where the central question of this entire investigation starts to come into focus. Because if TOI 452b really is a water world, with a substantial fraction of its mass locked up as liquid water, sitting in a temperate zone around its star, then the question stops being purely about geology or planetary formation. It becomes a question about life. We know with certainty that liquid water and life are connected on Earth. Every ecosystem, every organism, every biochemical process that has ever been studied depends on it. Water isn't just a habitat for life. On Earth, it's a participant in life. Solvent, transport medium, reaction site all at once. If a planet exists with a quarter of its mass as water, sitting in a zone warm enough for that water to remain liquid, the conditions that, on Earth, gave rise to the first living things, could in principle exist there too. But here's where the investigation has to be careful. Having the right conditions for life is not the same as having life. Consider what a world with that much water might actually look like. Not a planet with continents and oceans, like Earth, where roughly 7% of the surface is water, and 30% is land. A world where water makes up 25% of total mass would likely be almost entirely ocean. No continents, no land at all. A planet-sized ocean, potentially hundreds of kilometers deep, sitting atop a rocky or icy core. At those depths, the pressure becomes extreme. Water under sufficient pressure doesn't behave the way it does at Earth's surface. At a certain depth, increasing pressure can force water into exotic high-pressure ice phases, forms of ice that remain solid even at temperatures well above water's normal freezing point. Simply because the pressure is so intense, this raises an uncomfortable possibility. Even if TOI 142b has abundant water, the surface of that ocean, if it has a surface at all in any conventional sense, might sit atop a deep layer of high-pressure ice rather than a rocky seafloor. The kind of geochemical exchange between ocean water and rock, the exchange that many researchers believe was critical to the origin of life on Earth, providing essential minerals and chemical gradients, might never happen at all on a world like this. A planet could have abundant liquid water and still lack one of the key ingredients that may have been necessary for life to begin. This is the moment where the documentary's central question sharpens. We came here asking whether this planet harbors liquid water. We're leaving that question with a far more difficult one in its place. Even if the water is there, is it the right kind of water, connected to rock, capable of cycling nutrients, capable of supporting the kind of chemistry that life seems to require? Or is it isolated, sealed beneath layers of exotic ice, chemically inert, a vast reservoir of liquid that nonetheless remains lifeless? And there's a deeper layer to this still. TOI 142b doesn't orbit a star like the Sun. It orbits a red dwarf, the most common type of star in the galaxy, small, dim, and notoriously unstable in its youth. Red dwarfs are known for something called stellar flares, sudden, intense bursts of radiation that can be far more violent, relative to the star's size, than anything our Sun produces. Planets orbiting close to red dwarfs, which they must, in order to receive enough warmth to sit in the temperate zone, are also sitting close enough to be bombarded by this radiation. An 11-day orbital period means TOI 152b is far closer to its star than Earth is to the Sun. That proximity is what makes the temperate zone possible around such a dim star in the first place. But it's also what exposes the planet to potentially intense stellar activity. Could a planet retain a thick atmosphere, retain its water, retain the conditions necessary for life, while sitting that close to an active star? This is not a question with a clean answer yet. It's an active area of research, one where the same red dwarf systems that make small, temperate planets easier to detect also raise serious questions about whether those planets remain habitable over geological timescales. So now, the investigation has reached a strange place. A planet exists. Its size and mass have been measured with precision. Its density closely matches Earth's. Models suggest it could be a water world, with roughly a quarter of its mass as water, more than 25 times the water fraction of Earth. It sits in a zone where that water could, in principle, remain liquid. And yet, every step closer to understanding this world reveals another layer of uncertainty. Or could the same intensity be explained by rock and a thin gas envelope? If it is water, is that water connected to anything that could support chemistry the way Earth's oceans do? And if the conditions are right, can they remain right, sitting this close to a star capable of violent outbursts? Each of these questions doesn't cancel out the others. They stack, they compound. And this is, in some ways, the real story of the modern search for life beyond Earth. For most of human history, the question was simple, even if the answer was unreachable. Are we alone? Today, the question is fractured into dozens of smaller questions, each one a prerequisite for the next. Does the planet exist? Yes. Is it in the temperate zone? Yes. Could it have water? Possibly. Is that water connected to the planet's interior in a way that matters for chemistry? Unknown. Could it retain that water given its star's behavior? Unknown. If all of that works out, could life actually emerge? Completely unknown. Every yes reveals new unknowns behind it. TOI 152b sits at a particular point along this chain. Further along than most candidates, the size is right. The density is intriguing. The temperature zone fits. But the chain doesn't end here. It continues into territory that current instruments can only begin to probe. What makes this particular planet worth following isn't that it provides an answer. It's that it represents, perhaps for the first time, a real-world test case for an entire category of world that, until recently, existed only in theoretical models. Water worlds were predicted, calculated, modeled on paper, long before anyone had a planet that actually seemed to fit the description. Now, 100 light-years away, there might be one, and the tools required to actually find out. Instruments capable of reading a planet's atmospheric composition from across interstellar distances exist today, pointed at exactly these kinds of targets. This is where the story leaves us. Not with an answer, but with a planet that has earned the right to be asked harder questions. If TOI 45T2b turns out to be a water world, it would represent the first confirmed example of a category of planet that has, until now, been purely theoretical. A milestone, not because it proves life exists, but because it would mean an entire class of worlds, long predicted but never observed, is real. And if it turns out not to be a water world, if the density turns out to be explained by some combination of rock and gas instead, that result matters too. It would mean the models need refinement. It would mean the next candidate, and there will be a next candidate, needs to be examined with new assumptions. Either ways, something changes. And there's one more thing worth sitting with. TOI 152b is one signal from one satellite, surveying one small patch of sky around one star out of the roughly 200 billion stars in our galaxy alone. If a planet like this exists here, in this corner of the Milky Way, simply because the search happened to point in this direction, what does that suggest about everywhere else the search hasn't pointed yet? The transit method requires a precise alignment, a planet's orbit lined up almost perfectly with our line of sight. Most planetary systems are tilted in ways that make their planets invisible to this technique entirely. For every DOI 1452b that we detect, there could be many more, oriented just slightly differently, that we will never see using this method at all, which means the real number of potential water worlds in our galaxy isn't just larger than the handful astronomers have identified so far. It could be larger by an amount we currently have no way to estimate. 100 light years away, a planet sits in the dark, orbiting a dim red star. Its surface, if it has one, possibly drowned beneath an ocean deeper than anything Earth has ever known. We don't know what's down there. We don't know if anything has ever been down there. But for the first time, we have a real candidate, a real target, and the beginnings of a real way to find out. And somewhere in that uncertainty is the only honest place this story can end. Not with a discovery, with a question that just became a little harder to ignore.